你说你的 meeting 会去星期三，你觉得这周我们还要面？我问你啊，你需要吗？我不需要就你知道要做么就不面，还是什么意思啊？周三啊，如果周三的一点呢，就是上课前了，也是哦。
提取者，请启出话筒。
要再等3分钟，再等3分钟。没事啊。哎，所以我们终于要结束了，然后你们要毕业了，
找工作，
找工作了。
没打算简单吗？啊，没打算。有啊，但是我必须先完成你在那个毕业才可以出去。哎，你们就不用啊？我们要中国人要这边哦，就是哦，你不是这边4年，我这没有，我们也在，因为你是3年的，只是好，我们之前不是4年的，没有学校考我们明年毕业，但不是读翻译啊，是，所以你明年才走，是你这个是，这个，没错，我们也是这样说，啊，你们也是才好的，咋回国？应该多少也开始，
Cohomology 会，哎，我应该不会顺着讲吧，我应该是 like 抓重点讲，重要例子讲。
才200页，
Yeah，那边后面那个不会动到。我们最重要的是怎么用 coupler 去 detect 那个 homotopy，就这样。后面那些对题，嗯
就如果在红 space 靠模就比较觉得，
，coupler 它可能不会，它 ring structure 不一样，ring 的 structure 不一样，vector space 的一样，ring structure 不一样。Okay, let's start. Okay, today we will cover about cohomology ring. Okay, so cohomology ring will look something like this. Let's start, which is equals to the direct sum of every level of your cohomology. Okay. This product is slightly different. This product is slightly different, which we call the graded ring. So what's a graded ring? So graded ring, we can write it as a direct sum of an, where each an, each an are the additive subgroup. Okay, so meaning if you take two elements in AN, you add up them together, you stay in AN. But the multiplication doesn't stay on the same level, but rather it takes AK times AL to AK plus L. Okay, so you might see that AN is not closed under multiplication, but the whole A is. Okay, so the whole A is. Okay, so far any question about? Okay, actually we not just restrict to graded ring. Actually, our ring could be graded commutative or anti-commutative or skew commutative. Or I think we have to choose one if they commute up to a sign. Okay, commute up to a sign. Okay, so I mean for whatever you learn in like year one, most of them from year one, year two maths are commutative, right? But now here is commutative up to a sign. There's also a non-commutative one, right? Non-commutative. But here we'll mostly deal with graded and graded. This is due to the structure of the cut product that we had last time. And so cut product might not be commutative. Okay, so what are the examples of graded ring? So let's give some examples here. Well, I think in algebraic geometry, we already saw polynomial ring, or rather, maybe just AA1. The polynomial ring R adjoint A is graded, right? So how is it graded? What do you think? You write it just in terms of R times the monomial of wait, not like that, right? It should be degree less than or equals to n. Yeah. So let's not write it down. Degree less than or equal to n. Correct or not? Yeah. Right? No. I think we can. I think we can. Can or not? Let me think. I think we can. If I let me write this. I think we can write like this. Because you can split your polynomial into monomial time coefficient. Okay. And you multiply, for example, x squared multiply s cubed, you get s to the power 5. So you jump to the level of s to the power. Not only that, actually, there's one polynomial very frequently appear in cohomology is truncated polynomial ring, meaning you quotient out by some ideal generated by the power of n, n alpha n to the 0. So for examples, these are realized by some homology ring that later maybe I won't show you, maybe I'll show you, depends. Okay, so for example, this one, right, can be realized as the cohomology ring of RP2. Okay, last time I think we calculated this. We calculated this before. Because when it is RP2, I still remember now the cellular chain complex of RP2. This one must remember is coming up. So meaning you have one cell in 0 cell, one cell in 2 cell, one cell in 2 cell, and then the multiplication map is 0, 2, 0, 2, 0, 2, 0, 2. So if you just consider Z, right, it's not very interesting because the multiplication by 2 map is injective. So the kernel is 0. But if you mod out by 2, then every map is a 0 map. Then the cohomology is just the chain group itself. So there are 3 of them. Only up to level 3. right? 0, cell, 1 cell, 2 cell. Okay, so the third level, I mean the third multiplication will be 0 because there's no H3. There's no chain degree 3 chain portion or chain group. Okay. And this alpha here is the generator of the first cohomology. I think we showed this in class right last time. I use a simplicial cohomology. I use singular cohomology to show it. Okay, so this notation is degree 1 alpha is in degree 1 or dimension 1. In our case, we can think of it as a dimension 1 because it's an element in the one-dimensional co-cycle. So in general, actually, you can generalize this. You can generalize this to RPN. Okay? You want to guess what's RPN? The ring, the cohomology ring of RPN. Want to guess? Huh? Z mod 2 alpha quotient by alpha to the n plus 1. 2, 3, and then n plus 1. It's the same, right? Because here RPN, right, is like you have 0 up to the n cell, and then 0, 2, 0, 2, 0, 2, 0, 2, 0, 2, 0. And we can consider RP infinity. Okay, RP infinity. So RP infinity, you can imagine that there's no more quotient anymore. You know what's RP infinity? It's just a union of all RPN. A bit like taking limits. Next, we could actually consider CPN. Okay, so CPN, we can consider Z already because CPN by nature, you only have cell in the even dimension. Okay, so Z is enough to detect that the non-trivial chain, non-trivial cohomology that makes sense to do what? Okay, the relation is still the same, alpha m plus 1. Okay, but we can consider it in Z. No need to go Z mod 2. Go to Z mod 2 also can, but it's the same. We just change the ring to Z. Yes. Which one? Uh, Z2 alpha. Yeah. I think this case is commutative. Not every graded ring is skew commutative. Depend on what space you have. Okay. And actually, you can do more. What if I consider this ring? Do you think what space can realize this as a based on what we know before? What space can realize this cohomology? So we know that RP infinity can give me one alpha, right? So I can put a bunch of RP infinity together. So maybe I can get product of RP infinity. Okay. Okay. No. So now, when you look at this polynomial ring, right, you should think of some topological space that can give you these cohomology, these ring structure. We will talk about more on ring structure later. Okay. Yeah. So you think of this generator alpha I to be the degree 1 generator inside your space. Okay. So far, any question? Okay, so these are the polynomial that you see in abstract algebra. Right. Next, I want to introduce exterior algebra. I think you guys met it in differential manifold, right? Exterior algebra. This algebra turns out to be very important in this chapter. Okay, so let's define exterior algebra over a commutative ring. Okay, so what is this? Okay, so this is actually the free R module. Okay, so if I say it is a module or vector space, you should talk about the basis, right? So the basis here are the finite product of alpha I1 up to alpha I2. And it is associative and distributive on the multiplication defined by the following. So this is very different. So alpha I, alpha j equals to minus alpha j alpha for all I known j. Okay, skew commutative. Uh, but it's slightly different because our skew commutative rely on the degree, unless we set their degree as 1. Okay, but if they commute up to a sign. So in this case, this will imply that alpha I squared equals to 0. Okay, because alpha I squared equals to minus alpha squared. Unless it's Z mod 2, then it doesn't imply, but yeah. Typically, maybe I put typically here. Okay. Do you see this in differential manifold? The differential form. Dx squared dx is 0. Okay. So the identity element here is the empty product of alpha I as an empty word. Okay. Okay. So why is it important? So later we're going to see an example that actually this exterior algebra can be realized by the cohomology ring of a torus. Okay, we'll use torus to build this. I think last time we kind of see of the genus G topology. I mean genus G cohomology, but we didn't go into the example. So maybe today we'll do a torus version. Okay, so just now we told you a polynomial ring that can be realized by the cohomology of products of RP infinity. Now, here we use a n torus. I think we call it an n torus. Yeah, sorry. So n torus to realize this exterior algebra. Okay. So let's do one examples. Oh, before that, do you still remember what's the ring structure for this homology? What's the ring structure? Do you still remember? What's the multiplication here? Top product. Okay, so we take a top product. Okay, so let's do one example on torus. So again, we'll use the DW structure. Torus. Let's label it like this. V0, U1, V1, U0. Hmm. Hmm. What's the K? What's the N? This K? IK? Uh, so well, I mean like this can be like, I mean these I okay, sure. Usually what people will say is these I up to IJ is inside a set of 1 up to n. Like that. Because you just pick few of them up.
No, structure unique，
Unique, what do you mean?
我取不一样的杯子，给它不一样。
I mean, you take all of the finite product, all. You take the finite product, all possible finite product, all. Okay, so let's continue. So let's pick this CW structure here. Okay, is this a torus? Top and bottom, and then left and right glued together. Okay, so if you still remember, this H1 of torus, right? We doing Z? Doesn't matter. Okay, so this is isomorphic to form from H1 E Z, right? Okay. So what are the generators of H1T? Still remember or not? I mean homology of the torus. Do you still remember? Homology of the torus. Z and then Z bar Z H2 Z again. Zero. Zero or Z. Zero or Z. Huh? H1 is Z bar Z.
Yeah.
H2 H2 is Z. Is it? Okay. But we just care about H1 now. So the generating cycle here is A and B. Okay. So for this isomorphism, right? What we're gonna do is we're gonna correspond the one core cycle here to this A, B here. Where the map will send A to 1 and then B to 1 like that. So meaning it's a door to these map here. Okay, maybe I need to write a bit more. So first map is sending B to 0, then the other map sending. Okay, so we let one core cycle here to correspond to x2 on the other side. Ah, just okay. Okay, so far so good. Okay, okay. So well, so we want to figure out what's the so our question is what is the cohomology ring of so okay, so these are the two generators. So maybe we can try and check What is alpha cap beta? Okay, what is alpha cap beta here? All right. So in that case, maybe we can consider this two phase here, V0, V1, U1 minus V0, U0, U1. Okay, so meaning I take a linear combination of these two phase. Okay. So can you realize that actually this phase, this is a cycle. This is a cycle in H2. Okay, so this is a cycle in H2. Why is it true? Well, you look at the partial of this Z. Okay, you look at the partial of this Z. If you look at the partial of this Z, right? So one of it is V0, V1, U1, so this one. And then the other one is V0, U0, U1 is this one, okay? So you compute the phase. This is cycle in, sorry, this is a cycle in H2. Just now we say that there's something inside here. Okay, maybe you can verify this, okay, quickly. So maybe you get B minus A plus C minus A minus C plus B. Okay, okay, so you take away the first vertex, right? And then positive, take away the second vertex, and then negative. Like that. Did I do the wrong computation or not? So V0 and then V1. Okay, let me see. Do I get minus C instead? This one is minus C, this one plus A. So let me try. So minus C plus A. And then take away V0, get A. And then U0, get plus C. And then U1 minus B. Yeah, okay. I think this is correct. Okay, throw this away. Okay. Okay, so this is a cycle in T. But now, uh, we can look at the cup product apply on this two cell here. Okay, what do we get? Okay, what we get was alpha A times beta B, right? Because you take the, you split, right? Still remember? Split the two cell into two one cell. And then the other one is alpha A. What am I doing here? What's the formula of the cup product again? Why I got the minus here? What's the formula for cup product? Yeah, so this is just the cup product. Why do I got the minus? Yeah, cool. Okay, so I forgot. So because our Z is a linear combination of these two, right? Okay, so your cup product will be linear of these two. Okay, so first one you split V0, V1 alpha, and V1, V1 beta, B. And alpha on V0, VU is B, V0, U0 here, B, and then U0, U1, A. Okay, so minus alpha B and then beta A, which is 1 times 1 minus 0 times 0. Okay, because alpha and beta are the dual to A and. Okay, so what does it mean here? Okay, meaning actually if you can check, actually alpha cup beta is dual to the Z here. Okay. So it actually follows that. alpha cut beta will generate H2P. Okay. And in fact, this is a homologous, cohomologous. Sounds like a bio word. Cohomologous to Z2. This one need to check out, but yeah, cohomologous. Okay. So this cohomologous means if they are agree in cohomology, we say that they are homologous. So if agree in homology, they are homologous. Okay, so because things will be the same out to boundary, right? So up to boundary, they are homologous. Homologous cell heterogous. Okay. Anyway, so what's the ring structure here? So in this case, so what's the ring structure? There's no more to compute, because there's no higher degree homology, so there's no higher degree cohomology. Okay, so we have enough cohomology element in our ring. So we have, so alpha square will go to 0. Have we checked this before? I think we haven't, but you can directly check. You can directly check. Okay, alpha square. So meaning, I mean, like if you look at the split of these two term of two cell, right? Okay, these are the possible two cell you have now, right? So if you have alpha alpha on all the spots, right, obviously you get 1 times 0 minus 1 times 0. So you get 0. Okay, beta square is the same. Okay, and then just now, what do we get for alpha beta? We get 1. But if you swap the order, actually you get minus 1. Can you imagine? Can you imagine? So if you swap the order, you actually get minus 1 because minus 1 survive. So you see, this minus sign is very important here. This minus sign. So this minus sign actually comes from the cycle just now. Okay. So this minus sign here will give you a relation that alpha beta plus beta alpha is 0. Okay, so this is the exterior algebra generated by alpha. Okay, does it make sense? Okay, so although your ring is commutative, but due to the cycle condition, the minus sign will pop up. Okay, pops up. What time is it? Shall we do more? You want to see climb bottle or RP2? Want to see climb bottle or RP2? Both. Both. Okay, let's try. See if we can finish on time. Okay, let's try climb bottle. Climb bottle is very similar, right? It's just that we swap uh, one of the uh, one of the arrow, right? So B go up, B go down, and then it's the same. Okay, maybe you feel weird that I label all of them as V now. So just now we haven't identified them, but now we identify them for the purpose of labeling. So you should always remember that when are you like identifying them. Okay. It's okay, depend on how you want to label them, but make sure you know you are doing before identification or after identification. Or the purpose of labeling them. Because if you just put V, right, for the just now the cases, I want to label the face, I also cannot label the face. V, 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 which V you are talking about, I don't know. Right? So make sure you know when are you gluing them. Okay, so in this case here, we are not interested in Z anymore. We're interested in Z2 coefficient. Okay, because to make life easy, you will see that how our life will get easier with Z2 later. Or now actually. Okay, so in this case here, actually the claim is, yeah, So the claim is A, B, C will live inside the cycle of K of Z mod 2. And then so let's call this two cell U and L. So U plus L will be a cycle. Yeah, maybe. Sorry, not the core cycle, cycle. I think, did we write this down before? I think last time we compute one is coefficient Z, right? Okay, so maybe you need to try with Z2 to see this. Okay, so then we can try and compute what are the boundary map on these dual elements. Okay, so we can maybe compute all these. We want to try and compute together, see what happens. Let's check the boundary map on all these duals. And then we're gonna try and find what's the one co-cycle. Okay, so what are these? So basically you apply A dual to the boundary of U. So what's the boundary of U? It's actually A plus B plus C. So you notice that there's no minus sign here. Why I don't care about minus sign? Because our coefficient is Z mod 2. Okay, I just care, you just put everything to plus. In this case, A dual is something that only take number one at A. Others are zero. Okay, this is the meaning of dual. So you get one here. Okay, so similarly, if you compute all these, you could imagine what's the solution. What's the solution? Actually are all one. Okay, because the boundary of U and L are the same. ABC. Okay, and then dual only take value one at one of the one cycle. So what's the kernel here? What do you think? What's the kernel here? This is a linear algebra question. What's the kernel here? Can you build kernel out of these three elements here? There are three elements here, right? There are three elements here. What are the kernel? What's the matrix you should look at here? I think it's 1, 1, 1. 1, 1, 1. Yeah, so you should have two free variables, right? Okay, so you get A star plus B star or B star plus C star. 1 plus 1 is 2, so 2 is 0. Okay. And then can you see what's the image of del 1 here? Maybe these are del 1. Okay, what's the image? Huh? What? Sorry? Z? What's Z? Where's the Z? There's no Z in this part. So you can see that these are the map that operate on U and L, you get 1. So what are the map that operates on U and L, you get 1? The U dual plus C dual, L dual, right? These are the map that operates on U and L, you both get 1. Okay? So this operate on U, here get 1, here get 0. Operate on L, here get 0, here get 1. It's the same. Okay, so we're actually asking about what's this map here. Actually, it's U dual plus L. Okay, because they get 1 on both U and L. Are yeah. Anything else? Okay, so note that there's no C3. Okay, so hash 2 is just everything. And then multiplied by this image that we found here. So this is actually Z. Okay, you can change your basis. Change L to U plus L star, then you get Z. 喂，Hello，你吓到外面的人。弟弟还没有跟你来，是生病。OK，是生大病。好像最近很多人生病，学生也是生病。哦，OK， then what is H1 then? H1 H1 is just what we had. There's no image of del zero, man. Interesting. I didn't check. Maybe you can check first. Didn't check last time, but it seems that H1 is just generated by these two. Otherwise, we need to ask what's the image of del zero? What's the image of del zero? Del zero is zero. Why? Del zero is zero because if you look at the boundary map of H1, right? Boundary of H1, the 2 point is the same. So you will always map your one cell to zero. So del zero actually is zero. This part here actually is zero. Okay, good. So now let's look at the cut product calculation here. Here a bit different, the cut product. So now we'll look at the cut product calculation. Alpha cut alpha. And then maybe we can try alpha cut alpha on U and L. And then beta cut beta on U and L. Maybe you can try and calculate together as well. Try and see what are they. Beta cut beta on L. Alpha cut beta on U. Alpha cut beta on L. Beta cut alpha on U. And then beta cut. Okay, so U split out to what line and what line? Let's see. So the first line is B, second line is A. Okay, and then L, first line is A. Sorry, first line is C. C 的好像 V 一样。C, and then second line is B. Okay, so remember this, CB and then BA. Okay, so we're gonna do all these. So U is CB or BA? BA. Okay, and then I changed notation, huh? Oh no, I changed name. Did I change name? Yeah, I changed name. Okay, so L CB. Okay, alpha C alpha B. OK，不然你算一算，要我算你算，算看算完全部。You calculate, tell me the answer。就一堆的 binary 数字的。Sorry，回到上面，看去哪里？这里。嗯， 来聊一声算了吧。诶，不可以这样慢的。来，A 卷算。来，第一个竞胜，答案什么？你 guess 什么 AB？什么 BC？看这个，看这个，看这个。Alpha is A dual plus B dual。right A dual plus B dual add on B 拿到什么？来试下正确。A dual plus B dual add on B 拿到什么？啊，完了，对，完了，因为零加一嘛，一哦。连这个呢？Alpha dual plus B dual 在 A 呢，也是 one 呢，因为 one plus zero 啊，对吧？所以这个东西是 one 啊next is zero，对，zero times one which is zero，对，没有错。下一个呢贝塔 CB 啊，贝塔 BA，对，这个拿我，嗯，一个是 one，还有一个是 zero，所以你拿 zero，另外一个呢，对吗？So one times one 拿到 one，OK，and then 继续算，继续算，继续算，I think 你会拿到0.010，诶，这样就错了哦，错吗？嗯，Well，有没有人可以去找一下这个 Cohomology ring 是什么？因为我这里写的答案是 alpha square beta cube 跟 beta square alpha，但是呢，但是我们的 alpha cap alpha 不是零诶，这不是很糟糕？看一下我有没有记错东西，定我没有诶。U 的 first 第一条是 B 嘛，第二个是 A 嘛，C 的 L 的第一条是 V。I think 这个 label 是 OK 对不对？有 follow orientation right？说这个是一，这个是二，这个是三，这个可以放四吗？OK 啊。嗯，What's going on? Let me see 啊，CB BA。Supposingly 这个应该是零诶，如果这个不是零的话，beta 应该是零，这两个都不是零，这么神奇吗？怎么办？还是这个是个 Q？应该不是吧？Don't believe it。诶，有没有人要 check 一下？Cohomology of a fine bottle in Z2 长怎么样？还是要做一点 trick？看一下 relation 一样吗？我看漏了这个，对吧？找到吗？哪一个？为什么？ 好像这两个，I think but alpha and beta have different relation，有吗？还没做完，难道我们要 chain basis 吗？chain basis 也不可能啊。嗯，如果换成 AC 呢？可能换成 AC 就可以了吧？我觉得，然后换成 AC 就 is a good idea，有吗？这个把 alpha 变成 AC，把这个变 AC，这个，而且这个应该就是要的答案。try 看要不要？如果 AC 的话，这个就是零哦，因为它对 B 没有感觉嘛，这就是零。看下其他答案会变吗？A C 这个也是零，因为没有遇到 A。And then B 这些呢，这些中间呢会不会变？看一下这个 alpha，这个 alpha 对到谁呢？alpha 对到 B，beta 对到 A，还是零哦？对，因为 beta 对到 A 了。这个 C，原来这个是 B。哦，这个好像会醒来耶，可以给它醒吗？这个会醒来哦，这个会变一，这个应该就要睡下去了啊。这个会醒吗？诶，这个也会醒哦，这两个都醒来了哦。哪一个？哪一个？哪一个？杀杀杀！一个一个来，一个一个来。哦，跟我一样问题啊。对，我现在换掉哦，我要换去谁？我想要换哦，但是我换去 C 多也不太啊。BC 有了，我们有 BC 了啊？什么 B 乘 C？我们有一个 B 加 C 哦，还要一个，还有一个，还需要一个。嗯，我继续算看。beta，哎，sorry 啊，这个是 B 跟 A 哦，对啊，这个会醒来，跟 B 跟 A 对啊，这好像也有这个情况。那你的C 跟 A 这个还是睡的，但是这个醒了，会有影响吗？我想一想，这样不太一样，他给了吗？这样子就这样罢了，就这样罢了啊。你的是加，你这边加，你问谁？我不可以讲他们 contradiction 啊，我不知道他们的 basis 有没有，他们有跟你讲他选什么 basis？哎，因为我好像已经我记得我调过一次了，我漏调第一个，所以没有检查到第一个，我已经调过一次了这个答案。What's wrong here？就这样啊，切两个不了啊，这么来讲啊。好，哎，是。那个呢？Adrian，你看的那个 step 签下给你这个，interesting 啊，interesting。 Very weird. Let me see.哈，怎么样？S square y square 没有哦，没有这样多东西啊。你怎么？X square y square x y 2y 来的？我们哪里有这样的东西哦？2y 是零哦，在这个世界。我们是 Z mod 2哦，它是 Z mod 2。S square 和 x y 和
它的 y square 会和 x square 等同。
也不对呀、我们都不会等于零啊。什么事情呢？咋的？应该没有错吧？这个，嗯，没有一个是 square to 零哦。现在这个情况，还没来。假设我换去 C 才有啊，然后 B 的话就不会 square to 零。我现在有 alpha 去零啊，beta 去零啊，现在我要 confirm beta square alpha。So beta square alpha, what is it? So beta square 是一，beta square alpha，beta square alpha 应该要怎么算哦？诶，beta square alpha，上次我怎样算啊？beta 啊，什么？
来，
嗯哼，
把 K model 写成 RT2 HS1，它的 link structure 怎么样？
那是 RP2 HS1，
可以可以吗？不一样
也是下面
，OK 的对象
嗯
真奇怪啊，
因为就是那个水浆哎，哎，金色你是不是少了一个 B cube 在这边啊？你是少了一个 B cube，有没？哦，star A star 跟 B star 不够哎，A star 跟 B star 不够吧？因为你还有一个 C star 嘞。OK，but anyway，我看一下这个算得出吗？Let me see。说 beta square 再 cup 一个 alpha 是什么情况？Oh right，一定要是零，I guess。我想一下，说我们有 alpha、beta 加，诶，不对哈、嗯，哦，anyway，OK，我觉得 OK。嗯，I think 这个没有影响吧？我觉得是没有影响的。我想一下，我觉得这个对了，我觉得应该这个对了，我觉得这个应该对。Let me think。呀，我觉得这个对。OK，为什么对呢？因为 alpha square 是零，然后现在，and then beta cube 是零，because beta square 还不是零，cube 一定要是零，因为你去到 third cohomology 里面没有东西。And then这个0101 actually prove 了 alpha cut beta is a non-trivial element。OK，它们不是零，但是呢，beta square alpha 一定是零。为什么？因为 beta square 不是零，它是你乘了 alpha 过后，它要去到 third cohomology，third cohomology 是零。 这个东西要分，我觉得这个 OK 啊，你觉得呢？我觉得 OK。那个，嗯，一开始我给他这个，当我换对的 basis 过后，哦，所以我选的 basis 是 alpha star 加 c star 和 beta。可以 send 我一个 tutorial。
Yeah，他讲
Yeah，
A star 和 B star is also given H
啊，然后呢，
它算起来就是
嗯
它是 A Q B square A Q 减
，AQ AQ 减 b square，哦哦，AQ b square，然后 Q 减 AB
A Q 减 square 啊，
AQ 减 AB，它的 AB 是什么？
对，
那可能你 AQ 不是零了，怎么还有 AQ？减 AB 了，这样不是应该就减 AB 吧？然后 Z mod 2过后就变 AB 吧？对，你叫谁算？嗯，他算对吗？发给他，然后知错能改。什么是 E？嗯，哦，alpha K alpha 是 E。啊，我现在 alpha K alpha 是零了，我选那个 A star 加 C star 啊是零了，所以 A star 加 C star 它不会遇到 B 的，所以这边一定要有零，一定要有零，OK 吗？我觉得这个 OK 了，我觉得我 OK 这个 OK 了，你们 OK 吗？我 OK 了，我觉得 OK 了，因为之前确实真的有问题。你看啊，如果我之前的答案不是 alpha、beta 都是零，所以其实 alpha、beta 是一个 relation 来的，但是我没有加进来。但是现在改了过后，不是 alpha cat、beta 跟 beta cat 都不是 zero 来的，都不是被切掉的，OK 吗？对，没有错，没有错，没有错。哎，你没有看到我给你们看的那个圣诞树吗？看到了啊？对啊，有没有看到？哎，可是你没有看到 real analysis 的圣诞树过吗？那个 Riemann 跟那个 The Back，你们有看过 integration 的圣诞树？一大堆的那个 trigo integration 跟那个 by part 之类的东西在上面。OK，那个圣诞树哦，其实是 Morse theory 来的啊。给你看这个圣诞树，这个圣诞树是个 Morse theory 来的。I mean like 前面是你们学的东西啊，right？跟 genus 这个很出名啊，这个东西你可以去找找看，这个东西很出名。课本有吗？还
这里有
有哈、哦，是什么例子啊？很出名哦，这个你可以去看一下，你要看一下，可以很出名。他塞了很多东西在这边。这个已经是off link 诶，这个，这个是 Morse theory 啊，这个 chain group，这个 chain group 是 critical point，critical point。这个 boundary map，
不是没有
这个 boundary map 哦，它是 differential 哦，要在 mod 2的时候才比较好，才会是 mod 2的。这个 two form，two form，electric form，then 这个这个 two form 咯，two form 和 vector field
那个观众来
啊，是吗？
特例中的有什么？
可是这个是 two form 和
哦，
vector
对对，
vector
你这样写的，我记得，
Lie bracket
但是你这样写，
Lie bracket but anyway，这是从小红书找的小红书，OK，嗯，OK，我们就讨论到这边这个例子，还有问题吗？没问题，休息一下啊，5分钟。
啊，是这个，它是讲什么啦？这里在里面呢。Alexander Home Sphere，
真的荒废。
那个 solid color，
定义就是多的话，它就是比如说 E1 EI 的话，EI star 的 EI star 的意思就是它在 EI 的时候是 E，在其他地方都是零。basis 啊，它是那个多。
我看这反正很显
啊，你要看它的定义哦。
这就反正是什么啊？一大堆就是 tangent space 的 disjoint 到不是？我懂呀，
是它的 base space
我懂呀，完了。
啊，E star 就是它的。
但是为什么你有念到起来，它就一定是一单，一定是一三？
没有你 potential bundle 的定义是什么？这边有 tangent。
就还是我的就反正咯，还在把那个 double paper 拆成这个两的。
等一下，先 potential bundle definition 是什么？
接 double paper 一下子哦，还跑到没头去哦。
potential bundle definition。Wikipedia 好像奇奇怪怪，我看不懂，应该是没有 definition 没有。
但是不用不一样的东西哦，就是 shift 哦。
这边 potential bundle 是什么？它是 potential bundle of 一个 vector space 啊，我这边给它找一下 of vector space。之后它只是多吧哦。这样的话就是那个等于哦，它就是单 definition 吧哦，就是你 function evaluate 在那个 point 上面跟那些点啊，对吗？E star 就是 home from E 去那个，哦，就这样吧，就是你每一个点上面全部放 home to E to 那个。
或者是你在很多是 on 那个
No 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 no，我就讲不是这个意思啊，它可能就是纯粹就是 home 从那个出去吧，你不相信？What the heck？
我觉得它是一个 consequence。
你觉得是 consequence？
maybe 啊，对，
对啊，应该 tangent space of a vector space 是他自己，
一个 vector 变成 tangent space
是他自己，好像是自己。
是 R 吧？一个 R。
Rn 的 tangent space 就是他自己啊，他自己。
那个这样子。
Isomorphia，yeah。
一个 vector space 和 tangent space 还是这个。
那个 tangent space 你怎样去理解？还要讲定 define 呢？你要 derivative
是啊，I mean，如果你是这个 vector，
curve 啊，要用 curve，
你用 curve 只是其中一种。
但是全部是 equivalent 吗
这样包括 derivation 嘛？
？derivation 啊，这样也是 derivative 哦。
对啊，I mean tangent space 里面的东西就是一个 operator。
tangent space 里面也是一个 operator。
哎，如果你把一个 curve 这样点上有个 derivative，就是你再拿其中一个换一个 relation。 拿那个 function act 这个去提供，就给你一个一个就是 action 在那个点上面。
嗯哼，
那你把它看成普通的对这个，
它 is made of speed of curve passing through P at time zero。
你也可以这样理解。还有一个 classification 是用 curve 的，
对，因为不然的话，你不知道 define 什么是 derivative。
因为我记得所有 point derivation 的话，你可以写成一个 derivation of 一个 curve，所以他们是
嗯
等价的。
，OK，哦，你做了 curve 过后，你就可以做 derivation。
derivation 还有一个 derivation 你可以找到一个 curve。
我觉得他只是想 evaluate 它罢了吧，然后所以他叫 cotangent，然后刚好他的 tangent space 跟他是一样，isomorphic。
对，
我觉得他没有想要讨论他 geometry 的 structure 吧，他是个名字吧。
想要把它，
嗯哼
因为他们 paper 是有一个
，friend 哈，
frame 是不一样的，frame 是你要有两个 registration，然后你要有可以控之间的，
嗯哼嗯哼嗯哼
大部分只是
，V 之间有两个箭头
一个前后，还有一个一前面一个后的是，
，OK，
只是很神奇是那个 opposite 的箭头哦，的 representation space 就会变成更多，
OK，这有没有生气？
不是很神奇。那为什么？对，那为什么？
哎，你明天要背吗？啊，怎么说？看你啊，啊，你没有东西要讲啊？你自己做啊，还是怎样？
道理。
啊，明天的我还看我，我要定时间呢，因为他没有在嘛。你要的话，你可以提早来。你要啊，你10点来啊，下午就不要面啊。讲，
如果要的话，我就是这样。
如果你要，你是几时要？那你知道没有啦？你要跟我讲啊，你有没有来啊？我没有来，我不是不用在那边
你要打的
啊？
那我就
我没事。
他把它从头那里跑去，然后我从那里跑去。
对呀、所以我要把你们调上来啊，对吧？你没有东西要讲，你可以自己做。OK，等一下我再问。OK，不懂，我没有回哦，有回你们任何一个人吗？I don't know。有吧？他的那个 WhatsApp 那边有 history。嗯，
有时候靠
谁 call？你 call 他？没有，你要试一下，你等一下试试。OK，then 我们先继续先。OK，so 另外一个让你自己去看了哈。for 这个 RP2的，right？So this proposition is very important. So if you have a continuous map, then you will induce a ring homomorphism. There's no proof here. Should we find the proof somewhere or just do it? Okay. So once you have these, right, you can show that a homotopy equivalence induced cohomology ring isomorphism. Okay, so this is very important. So we're gonna use this to show that something is not homotopy equivalent. The ring structure is different. Cohomology group can be the same. Okay, last time I already showed you. Even their pi one is the same, Hn is the same, cohomology also the same. Okay, homology the same, homology the same. Okay, what's different is the ring structure. So ring structure is different, then they are not homotopy equivalent. Okay, now. Okay, so this means that the first proposition is very important. Maybe it's not hard, this proof. Is it hard? What do we need to show this is a ring homomorphism? F star AB equals to FA cap AB FB. I think this is what we showed last time, right? FAB is this one. This. I think we showed this. Yeah, I think this is the unique. This is what you need. Ring homomorphism, right? But I think you still need to check like what do you need to check for ring? F star 1 to F star 1. And then FA plus B to FA plus FB. I think that one is straightforward. Okay, but this one I think this is hardest one. Okay. Good. And then next is if you have a disjoint union of spaces, then your cohomology will split into direct product. And then if your space is a wedge sum, the reduced cohomology will split into direct sum of direct product of reduced cohomology. Okay. More than $. Okay. Yeah. Similar result. Skip. Okay, then I just go through some famous ring. We won't prove it, but I put some proof here. Okay, so this is what we have mentioned just now. Okay, RPN in terms of Z2 is Z2 adjoint A multiplied by A to the n plus 1. Okay, so I guess from here you should think about the usual polymer ring you learned in AA and then see what space you can attach to them and they are homogeny. Okay, so if you go to RP infinity, right, there's no finite end, so that means your alpha won't disappear. They will stay in a different level of RP infinity because RP infinity consists of all the RPN. Yeah, 这个 proof 怎么那么长哈？这个 proof 呢，这个 proof 有几个 proof actually. One is you have to compute using cut product, actually relative cut product, or later you can use point correct duality, or you can use a more sophisticated item, okay, called Geising sequence. Hey Adrian, 你的 project 定了吗？还没有？你不用写啊，不用写了啊，不要写了啊，还没有。还有你们的那个，哎，你们的那个 AI 现在有点麻烦哦，你们要早一点去交啊。AI report，哦，I mean turn it in，要，怎么不要？你的 project 要配音话当然要啊，project 肯定是要 turn it in 的。对，为什么早？因为会有很多事情，怕的事情。
你不要 set 那个什么东西啊？
我没有 set，我没有 set，是你们的那个 class ID，你们要自己去弄，不是改 system 的吗？
是
你们要去那个什么叫什么 ASPR 还是什么 AGPR 还是怎么名字？什么东西啊？可以说你记得吗？No no，never try，haven't try yet。你们全部有收到 email 吗？turn it in 的东西有，I think 有啊，这块没有用到。OK， 你要去弄那个 turning in 啊，basically 就是你要去 sign in 那个in，你要 sign 这个 ASRP，我们的 ASRP sign in 了过后，那边会有 class ID 跟那个 password，你每天都要 refresh 用，OK，因为它的 quota 不够，所以它就 refresh 用。嗯，如果你的 AI report，如果你的 AI mark 超过20分，它会有写20分，then 你就要来找我。哦，不能，你不能找我。OK，你一交上去过后，你就要告诉我你几时交了，我才可以去 check 你的 AI 分有没有超过20分。如果超过20分，我就要拿你的那个 PDF 来我这边 submit，我这边我才可以拿到 report，AI report。把你们是可以拿到 turn in report。OK，说你 submit 过后，你告诉我你 submit 了，然后我就去 check 你的 AI 分，但是我要等到第二天才可以啊，因为这是 manually assort 的那个 data，因为他们把全校的人变成一个 class 或者几个 class，然后他们会 update 那个 list，我要去 check，每天的9点，就拜一到拜五啊，拜六礼拜你交，你就要等拜一了，因为还没有做工。不然你就直接交给我也可以，
嗯，
嗯，或者通过学校，
然后才拜一到拜五啊，
对啊，
然后只有早上9点才能。
那是 librarian 的我 office 啊，不是我 turn in 没有信息，嗯，
只要交这里面就够了。
什么？
只要交这个电脑那个一品。
对你交这个你有 turn in report，但是你没有 AI report，OK？你交了过后你要告诉我你交了，我要去签你的 AI 分，对，第二天的9点，对，如果你的 AI 分超过20分，then 我就要去拿那个 report，你就要交给我，我再去交一次，我拿那个 report 上来。然后你才再回去改啊？什么什么一样？就要告诉你你哪里东西像 AI 哦，你就要改哦，对吧
嗯，是
？OK，Alright，说为什么这样难哦？它把它 split 成两个open set，你说它的 proof 啊，为什么这样难？所以你看它会有用到 chart 的，哎，sorry 啊，它会用到 chart，你看它会用到 chart。以前呢，我看这个就是看到很 blur，死不 blur，就是在 RPN 的 chart 哦 chart。就是它的那个我们叫什么啊
不然做不到做我是联盟。
对呀、我们是叫它 chat 吗？还是叫什么名字啊？我们是叫 chat 吗？
哦，
我们叫 chat 吗？好久没怎么去？是啊，是叫 chat 的。OK，对，所以我们看不同的方向嘛，对不对？And then 以前我就是看不懂这些东西，你知道，所以 that's why 我们会想要在那个 Algebraic geometry 里面做多一点 那个 projective space 的东西。然后它有用什么呢？嗯
难怪你要
，blowout 是我 PhD 做的东西。projective space 是读这个的时候很 blur，我们老师从来没有教我们的，然后直接用吧，就是很 blur，不知道怎么来。然后 torus 也不知道有动还是没有动，还有没有动，就是你不知道是填满了 torus 啊，还是那 sphere 也不知道是填满还是没有填满，他就画一个那个嘛。How I know？那时候我都不会 sphere，他只讲 sphere，我哪里知道他讲什么 sphere？因为我教你了嘛，他没有教我，我都不会，对吗？我都不懂，我就是 blur 啊，confuse 啊。他没有用 ball 这个字，他直接 sphere，我哪里知道还要 ball 还是要什么东西，对吗？西北 confuse。Sorry Taurus 啊，有名字没？没有名字吧？就 Sorry Taurus，就很 confuse 啊，这个观念没有搞清楚啊。 他就直接用吧。Anyway，就每一个 SEM 都在 repeat 这个事情。analysis 的时候，然后又进到这个 topology 的时候又很 blur。analysis 是用什么啊？然后很 blur 啊。有啊，不是有吧？那有。那比如说给你们做那 topology 的 example，不是有那个 RPN 在里面，还有 sphere 啊，有时候会遇到 sphere。Anyway，就这样咯。Right, so 因为我们有 RPN，we have RPN，we have CPN，then we can go to quaternion 咯，and then you can go to octonion 咯，right? Quaternion, yeah. Then you can see that actually quaternion is a fourth degree dimension, okay, instead of even, and then octonion will be 8 degree bar, if not wrong. But this one not important, just for fun only. Okay, let you see here. This one quite interesting. Let you see. What if we switch back to Z? If we switch back to Z mod 2 to Z, what happened to our RPN? Okay, so you can see that you will be quotient by 2 alpha, okay, because previously this 2 alpha disappeared due to the mod 2. And then if you look at the odd version, you have a extra beta square and alpha beta. Okay, there are much more relation coming up. And then for RP infinity, you just left with 2 alpha. Okay. So in Z, you have more relation coming up. Okay, I think next part is important. Next part is what we're gonna test on. Yeah, next part. 这种类型的题目。Yeah, next part 我们可以讨论一下。I think you can remember this as a fact, this ring. Okay, so let's do the next part. Okay, we want to show that CP2 and S2 wedge S4 are not homotopy equivalent. Okay, this is what we want to show. Okay, so we can use what we know previously from previous theorem. We know that H star of CP2 with respect to Z is ZB and then quotient out by B cube, like that. Okay, so far. So this beta is degree 2 element. Okay, you only have 0, 2, and 4 for CP2. At the same time, what about let's talk about reduced version of S2 wedge S4 first. Let's talk about this reduced version because we know that the reduced version of this can split into direct sum. Okay, reduce on wedge sum can be split into direct sum. Okay, so what's the difference between reduced and unreduced one? Do you still remember? What's the difference between reduced and unreduced? Reduced one we throw away H0. So H0 part become nothing. Okay, the identity is thrown by you. Okay, you throw away the identity. So maybe you can write it in this way. What's the cohomology ring of X2? This is very important. Okay, this one appear in my paper. What's this one very important? Very standard thing. What's the cohomology ring of S2? How about what's the cohomology of S2? It is non-zero at the 0 and degree 2. Okay, but we have reduced, right? So meaning what? We only left with the degree 2 thing. So degree 2 thing here. But then if you consider the cup product, you should get to 0 because there's nothing else already. If you cup them, you should go to degree 4, right? There's nothing in degree 4. Okay, similarly for S4, you have a degree 4 generator. Okay, and then you cup it, nothing already. Okay, so in this case, what we see was if you look at the unreduced one, okay, you will retrieve the truncated polynomial ring. Okay, you can retrieve the truncated polynomial. So you put back your identity, you put back your degree 0 in. Make sense so far? So far makes sense? Okay, and moreover, so here is more important thing. Alpha square is equals 0, gamma square equals 0, and what do you think about alpha gamma? Any degree, any element of degree there. Alpha is degree 2, gamma is degree 4, 4 plus 6 is degree 6. Anything inside degree 6. If you look at this CW structure or cell complex structure or cellular complex structure, anything in degree 6. Wedge product or not times, not product, it's a wedge. It's a wedge sum. You only have degree 0, degree 2, and degree 4. There's nothing in degree 4, degree 6. Okay, so these two cut together should be 0. Nothing inside there. Okay. But then what? Sorry. Mega. Because if you take cut product of alpha between alpha, what do you get? A degree 4 element. If you cut product between delta, you get a degree 8 element. But there's no degree 4 or degree 8 in cohomology of S4, S2, and S4. Okay.单看 S2 的话，单看什么 ？S2 的话，它的什么是 zero？对，对，alpha square 是 zero。对，alpha square zero，所以我切掉。Okay, cool. Okay, but in this case here, because we try to assume by contradiction, right, these two are isomorphic, right? So I mean, like, we try to say that these two things are isomorphic. Well, I mean, like, sure. Wait, let me show you. Yeah. So, but what's the generator in CP2? The cohomology of CP2, the degree 2 generator. But the degree 2 generator here doesn't square to 0. Okay. Beta cut beta to be non-zero. Okay, so altogether, what do you get? H star S2 wedge S4. This is just Z of xy and then quotient out by x squared y squared xy. And then on the other hand, H star of CP2 is what? Z of one thing, alpha, right? Did I write like this? Beta, okay. Beta cube, okay? So you want to ask whether these two are isomorphic or not. Okay, actually it turns out that these two are not isomorphic. Okay, because if you want to have an isomorphism, right, definitely you need to send your B to somewhere. Okay, you should send your B to some of the generators. Okay, you cannot send to X, you cannot send to Y. You also cannot send to any combination of them. They are not isomorphic. Because on one side, beta squared to non-zero, but on the other side, xy was squared to 0. Or if you send both of them to x or both of them to y, also get descent to 0. What about the combination of them? You should also get 0, I think. So far, any question for this one? So since their cohomology ring is not isomorphic, S2 wedge, S4 and CP2 wedge. Sorry, just CP2 are not homomorphic. Okay, so this is a very strong result. So you turn a topology question into a ring problem here. Okay, you turn into some ring problem. So that's why people will think that, oh, abstract algebra is very abstract. Yes, because you don't have a sense of purpose there. But here we got a sense of purpose. We want to ask whether these two space is the same. Okay, so you can see, you can view abstract algebra as a tool. It's just a tool for us to check something else. Okay. Yeah. Let's see. Should we go to the next one? Maybe we can quickly go to the next one. So second, you realize that RP2n plus 1 and RP2n wedge x2n plus 1 have the same cellular chain, same cohomology, same homology. Is it the same? I mean, RP2n is a subset of RP2n plus 1, right? So what's the difference between these two? RP2n plus 1 has a n plus 1 component, right? 2n plus 1, sorry. But 2n plus 1 can be given by a 2n plus 1 cell, right? Okay. So you have a 2n plus 1 cell that map the boundary onto RP2n. Okay. So this is equivalent to, I cannot say equivalent. It's the same cell structure with RP2n wedge x2n plus 1. The boundary map is different. I don't know. Huh? No. Homeomorphic. Is it homeomorphic? 这两个 cannot be because we're going to show that it's not homotopy equivalent, so cannot be homeomorphic. It's just that they have the same cell, but the last attaching map is different. One of the attachment is you glue along the other one you have to send the boundary to one point. So this is the difference between them. The attaching map is different. So turns out that this attachment is different, but you can compute the same homology and cohomology. Okay, makes sense. Okay, so why are they different? So we just compare their ring structure. So one of it by formula or by theorem, we got this. Okay. On the other hand, what do we get? Let me see. So on the other hand, maybe we can talk about the reduced version first, and then we can recover the unreduced one. Because the reduced version is very friendly to wedge product. Okay, it's very friendly to wedge product because we can write it as a direct sum. So then what? So then later we just add in our H0 is enough. But H0 is very easy to add. Okay, so if we split into these two, so we just need to care about what is the H star of RP2n and the H star of S2n plus 1. Okay, so what are these? So one of these is Z2 beta and then beta to the 2n plus 1. this beta is degree 1, and then the other is, let's say, is a gamma, but this gamma is in degree 2n plus 1. Okay. So if let's say there's a ring isomorphism, right? Okay, what we're gonna do is we, for example, so there's really one generator on this side, right? So here we got two generators, okay? But that one is degree 1, right? So we're gonna send the degree 1 to degree 1. Okay. If we send this suppose f 2n plus 1 to rp 2n wedge x 2n plus 1 here. This is an isomorphism. Sending x star b to alpha. Okay, so what do we get here? Then if you check 0 here, which is f star of 0, but on the b side, right, we know when b can get to 0, which is 2n plus 1. But if you apply this isomorphism, your alpha 2n plus 1 is 0, but your alpha only get to 0 when power is 2n plus 2. Okay, too early already. Okay, too early go to 0. No contradiction. Okay, does it make sense? So the idea here on this trick is you write down the homology on both sides, and then suppose there's an isomorphism between them, and then you get some contradiction out of their degree. I mean, no, sorry, out of their order, right? Their order. Yeah. Is it order? Order is something going back to identity, right? This is something go to 0. What should we call it? On their relation. Okay, something wrong with their relation. Okay, makes sense. Yeah. So for example, here you also should send to the right degree. For example, here the x and y, x is degree 2, right? So you should think of b sent to x. When b sent to x, then x squared is 0, but on the other side, b squared is non-zero. Okay. Any questions so far? Okay. You are feel free to use the comoduling of the real projective space, complex projective space, and so on. And these are simple spaces. But what I want you to realize is their degree is different. So if they are isomorphism, then there will be a contradiction to when they get to 0. Yeah. Okay. Any other question? Or question or not? There's a remark in your textbook. Maybe we didn't cover it, but they say that the cut product can be used to distinguish infinitely many homotopy class of map from S4n minus 1 to S2n. And this is what they call a Hopf invariant. Yeah. Yeah. We won't have chance to cover this Hopf thing, but okay, so far question. For the rest of the 100 pages, right? I think one thing we will go into detail is Kuhn formula, because that's about talking about the comoduling of product space. I think that's the last thing we want to cover for this technical part. And then point correct duality, we will just mention it. Actually, point correct duality can give you very simple combinatorics equation here. Okay. Yeah. Instead of using the n factorial over factorial times n minus k factorial, but then we can use space to see this. We can use Betty number to see this. But I don't think I will tell you how to compute this formula. This is very important. Hey, it seems like I haven't finished writing this part. Let me go back and check. Yeah. And then I mean for point cardinality, something that I want to tell you was orientation stuff. Okay, maybe you want to make precise what orientation means because I think you have heard orientation in various classes. So we want to try and use homology to tell you what's orientation. And after that, we don't really go into some very technical stuff. But I will show you some very interesting construction. For example, like the CAP product. So CAP is like doing homology and cohomology together and then become a homology. And what else? And then I think more importantly, we will introduce what is point cardinality. There's some very interesting calculation as well. See how it goes. If don't have chance, then I just leave it for you. Yeah, but have you like for example, maybe for example, if you look at this triangle, right? Like maybe you can make this make this vertex into edges and then make edges into vertex. You can see that it's another triangle again. You wonder why? You wonder why? Yeah, there is a why here. You turn a 0 cell into 1 cell and then you turn 1 cell into 0 cell. Why is it still a polygon? Or maybe why is it still a triangle? Polygon may be quite obvious. Okay, there's something to do with this point duality. Sometimes we call these a dual cell. Dual cell. Point dual cell. Okay, we'll see how it goes tomorrow on the Friday or Wednesday. Hey, for your typeset, right? When do you want to submit? Friday. Is it okay? Friday. You submit your corrected version there. This Friday. 可以吗？什么？没有。有什么好 revision？你要 revision？真的吗？你这样厉害，你还需要 revision？
没有 revision，民主社会代表大家的意见。
你们自己几个月在 revision？有什么好 revision？你要做什么 revision？你说说他要做什么，我才可以做嘛，不然不做你叫我来做嘛。天我拜四会给啊，还有拜三会给。应该不太可能，不太可能吧？我已经给完了，给完了，我会给完。
差最后一步给
什么？你要那张 paper？
这个连那个解答到最后一步，那我们猜最后一步。
这么夸张？不，你再想想看呢？因为你现在给我拿 revision 的话，我不能够记到那个 workload 里面，然后我们也没有 book 到房间，就要另外 book。book 房间还没有 book，然后再看到拜三再看，觉得怎样？我拜三会给你的。Oke, ada apa lagi?
还有
862，
还有
862，OK。Text file 你们整个 zip 加上去，看看够大吗？交得到吗？试看，你们 zip 交上去。 OK，不懂，暂时没有人空白吧？
就给我去跑。
你来得及了？
那
没有啦，考试前应该是没有人做了，
对对对，
大家都很忙。
礼拜超门关，
嗯嗯哼，
如果读不懂，我超级嘞。
书都读不懂，
嗯，
很正常诶。
完，
当然没有。
你们这个学期才开始读不懂
A G 我也读不懂啊。
A G 有一点，
A G 一到那个 blue 那边，
主要 A G 后面两个签会有点，
傻眼那个。
嗯，因为那两个我觉得可以单独做课。
你终于上了
单独开课。
A G 的后面两个签会还有课，
正常啊，太多了。
嗯，那
他不
个
干脆直接写。
拿其中一个就好。嗯嗯，没有开啊，但是没有开。
问你有没有吧？
啊，有。